Antimatter. The electromagnetic spectrum is the collection of all possible wavelengths of light and electromagnetic waves. Gamma rays have the shortest wavelength, radio waves have the longest wavelength. Planck and Einstein said that light comes in particles, and those particles are called photons. The energy of a photon is given by Planck's constant times the frequency of the photon. So Planck's constant is 6.6 times 10 to the minus 34, and that times the frequency gives you the energy in joules. If you want to use this equation, but you've been given the energy in electron volts, you need to turn the electron volts into joules to use it in the equation. So 1 electron volt is 1.6 times 10 to the minus 19 joules. So you times the number in electron volts by 1.6 times 10 to the minus 19 to get the energy in joules. Paul Dirac was a famous English physicist, and he was trying to combine quantum theory and special relativity. Special relativity says that nothing can travel faster than light. Dirac came up with this equation, a famous equation in physics that's now called the Dirac equation. The Dirac equation is a little bit like a quadratic equation. So just like a quadratic, say if we've got x squared minus 4 equals 0, there are two different possible solutions to that. X could equal plus 2, because plus 2 times 2 equals 4. But x could also equal minus 2, because minus 2 times minus 2 also equals 4. The Dirac equation is the same. Dirac was trying to account for the properties of matter particles around him. But what he realised was that there was always a second solution to the equations, which he called antimatter. These were particles that had the same mass and energy, but all of the opposite quantum numbers. Turns out that Dirac was correct. For every particle, there's an antiparticle. So the proton has an antiproton, the neutron has an antineutron, the electron has an antiparticle, which we call a positron. For every antiparticle, it has the same mass as the particle and the same rest energy as the particle, but it has the opposite charge and opposite other quantum numbers. So for instance, a proton has a relative charge of +1, an antiproton has a relative charge of -1. Theoretically, you could have atoms made of antimatter. So you could have an antihydrogen atom where the nucleus was made of an antiproton, and instead of an electron going around the nucleus, you would have a positron going around the nucleus. And those atoms would behave just like atoms of matter do. In reality, in practice, we never see atoms made of antiparticles. So you could have whole objects theoretically made of antimatter. So if you were to meet your antimatter self and shake hands, it wouldn't be very pleasant, because you would both explode. All of the particles would annihilate with the antiparticles in your opposite self. The particles would be destroyed and turned into energy. This process, called annihilation, is important to understand. So matter and antimatter cancel each other if they interact, and then mass gets turned into energy through the equation E equals mc squared. It's important to note that a particle of matter doesn't annihilate with any particle of antimatter. It only annihilates with its opposite type. So an antiproton can't annihilate with a neutron. So a proton can only annihilate with an antiproton. Today, there's almost no antimatter in the universe. It's only created in particle accelerators and high-energy cosmic ray showers in the upper atmosphere. So for example, if we have an electron that collides with a positron, both particles will be destroyed and they'll be turned into energy. That energy will be in the form of photons. It turns out that to conserve energy and momentum, which laws of physics say you have to at least create 2 photons. So you can't turn a particle of matter and antimatter into just 1 photon. You have to make 2 photons. The total energy before has to equal the total energy after. So the minimum amount of energy that the photons are going to have is the rest energy of the particle and antiparticle. So if we add up the rest energy of the electron to the rest energy of the positron, that will give us the energy of both photons combined. So for example, a proton hits an antiproton and turns into a gamma ray and another gamma ray. So the energy before equals the energy after. The energy of the proton and the energy of the antiproton are both 938 mega electron volts. That's going to equal the energy of the photon plus the energy of the second photon, which we can write down from our equation as Planck's constant times the frequency. Remember, we have to turn the energy in mega electron volts into joules. So we have to times that by 10 to the 6 to get rid of the mega, and times by 1.6 times 10 to the minus 19 to turn it into joules. That equals 2 times Planck's constant times frequency. So we can rearrange to work out our frequency. So why isn't there any antimatter left? Well, it turns out that in the Big Bang, when all of the matter and antimatter was created, there was a tiny asymmetry between matter and antimatter. That meant that matter and antimatter annihilated each other and turned into energy, but there was a tiny, tiny bit of matter left over. That tiny bit of matter that was left over is everything that we see in the universe today. Practice question. An electron and a positron collide and annihilate. The rest energy of an electron is 0.5 mega electron volts. What's the minimum energy of each gamma ray? And what's the minimum frequency of each gamma ray? So we have a positron and an electron that turn into two photons. The total energy before has to equal the total energy after. The total energy before is 2 times the rest energy of the electron. So that's 2 times 0.5 mega electron volts. That's 1 mega electron volt. We need that in joules to use it in our equation, so we have to times it by 10 to the 6 and times it by 1.6 times 10 to the minus 19 joules. That total energy equals the energy of both photons combined. So if we want the energy of one photon, we have to divide that number by 2. That gives us 8 times 10 to the minus 20 joules as the energy of one of the photons. Now we want the frequency, so we use our equation E equals hf and rearrange to find f. It's going to be 1.6 times 10 to the minus 13 divided by 2 divided by Planck's constant, which is 6.6 times 10 to the minus 34, giving us a frequency of 1.2 times 10 to the 20 Hertz. Pair production. Pair production is the opposite of annihilation. So in annihilation, two particles are destroyed and turned into energy. In pair production, energy is turned into brand new particles. But because charge has to be conserved and other quantum numbers have to be conserved, we can't just make a particle on its own. We have to make the particles in pairs so that the total amount of the quantum numbers stays as 0. So for instance, if we make a positron, we also have to make an electron at the same time, so the total charge adds up to be 0. So as an example, a proton and a proton could collide, and their excess kinetic energy could go into making a brand new pair of particles. So the proton and proton collide, and then after the collision we have our original protons, but the spare energy went into creating a proton and an antiproton. It has to be an antiproton because we have to conserve charge. The total charge before is +1 + 1, so +2, and the total charge after is +1 + 1 + 1 -1, so it's still +2. We didn't create charge because we had a pair of particles. So pair production always creates a particle and its antiparticle. Another example is a gamma ray photon. A gamma ray can turn its energy into a pair of particles. So for instance here, the photon is going to turn into a positron and an electron. The amount of energy you need to make those particles has to be equal at minimum to the rest energy of the particles. To have an electron, it at least has to have its rest energy. And since we've got two particles, the photon has to have enough energy to make two particles. So for instance, the mass of an electron equals the mass of a positron, which is 9.11 times 10 to the minus 31 kilograms. From E equals mc squared, we can turn that mass into a rest energy. So c stands for the speed of light, which is 3 times 10 to the 8 meters per second. If we multiply that by our mass, we're going to get a rest energy of one electron of 8.19 times 10 to the minus 14 joules. We've created an electron and a positron, so the amount of energy we've used up in creating the particles is twice that. So that's 1.6 times 10 to the minus 13 joules, or 1 mega electron volt. That amount of energy is the minimum amount of energy that the photon had to have. So in pair production, one photon becomes two particles. In annihilation, two particles become two photons. Practice questions.